στα αγγλικά, γιατί δεν πρόκειται λίγο καν στα ελληνικά και με την ορολογία θα τα μπερδέψω λίγο. Οπότε θα μιλάω στα αγγλικά. Αν έχετε κάποιες ερωτήσεις, να με σταματήσετε, δεν υπάρχει κάποιο θέμα. Λοιπόν, οπότε ξεκινάω. So I'll talk about my background first, just to introduce myself. Kind of final introduction. So I did my PhD on numerical optimization. I worked on Newton-type methods for some applications like signal processing and machine learning, logistic regression, and other regression problems. And I'm generally interested in the complexity of methods. I worked in complexity of Newton-type methods. And for Newton-type methods, I also worked on solving linear system, because when you apply a Newton-type method, you have to solve a linear system at every iteration. So I worked on developing fast methods, numerical linear algebra methods for solving linear systems for Newton-type methods. So after that, I moved to Berkeley, and I had two projects there. The first project was parallelizing optimization methods for machine learning problems, and this is what I will talk about today. And also I worked a lot on a subfield of network science called local graph clustering. And I'll talk today how optimization is related to that subject, and what we can do better or we can do right now, and some open problems. Okay, so I will start with parallel methods for convex optimization. This is work that I've done with people at Berkeley. These are two papers that we have, IPDPS and scientific computing. So let me start by introducing the problem. So we have to minimize the sum of two functions, the function g and the function f. Lambda is a parameter that controls the trade-off between g and f. And usually f is some fidelity function. It measures, it's a loss function. For example, it can be the least squares function or the support vector machine function. And g is some regularizer. In this particular case, the examples that I'm showing is g is the L1 norm, which is generally a sparsity inducing norm when we want the optimal solution to be sparse, have a lot of zeros in there. And other examples is group lasso and elastic net. So depending on what regression problems and classification problems like logistic regression, they are all formulated this way in terms of optimization. So I will make some assumptions just to simplify the talk a lot. So I will assume that we want to solve L2 least squares problem, and we will assume that the matrix A has more columns than rows, and it's partitioned row-wise. So we have some batches of rows, and we send them to some processors, because we want to parallelize the method, right? So, and I will focus also on, we'll assume that we'll always work on a single coordinate descent method, and I will explain briefly the method, what it does and how it works. So these are some assumptions to simplify the talk. In general, the results I will talk about, they hold for, we can show similar results for column partition and more complicated block partitions. And the performance depends on what the data set, the sparsity of the data set, if it's in condition or not, and the method that we are using. Beyond coordinate descent, the results I'll talk about, they hold for block coordinate descent methods. Instead of working on one coordinate at a time, we work on multiple coordinates at a time. Accelerated block coordinate descent methods, which are optimal in terms of complexity of the method. Newton-type methods, which I call first-order plus+, that means that we don't use just first-order information to make a step for the algorithm. We also try to use second-order information as well from the objective function. And proximal versions, meaning that specialized methods for particular regularizers like the L1 regularizer. Okay, let's start with an example of coordinate descent. And what is coordinate descent? This is a data matrix, and at this iteration, this is a randomized method. At this iteration of the method, we have to pick one column of the data set, or one feature, or one variable, depending on what terminology that you're used to. And let's have a vector EK that denotes It's an indicator vector. It denotes the coordinate that we chose at the kth iteration. So like every optimization method, coordinate descent, we have to make a step in order to update the parameters xk. And in this particular case, the step is defined as ek times delta xk. So the question now is, how we select delta xk? So since the L2 regularized problem is kind of trivial, one thing that we can do is try to minimize the objective function along this chosen direction delta xk. So we minimize this formula here with respect to delta x, and it has a closed form solution, which is essentially the step size times the partial derivative of the objective function. So now this is the method. There's a question here: how do we parallelize this method? Because if you're working in a serial environment, all you have to do here is a few inner products to compute delta xk, some summations and trivial operations like this. So every iteration is extremely cheap. It only requires two inner products, but the method requires a lot of iterations. So when we go in the parallel setting, that will translate to a lot of communication cost among the processors in order to guarantee convergence of the method. So as I said, when we look at the formula, we have two major kernels here, which are two inner products. The first one is for the step size, which is an inner product with a chosen column with itself. And the other one is essentially the partial derivative computation, which is also, it relies on a simple inner product. Okay, so how will you maybe implement this in parallel, right? So one way to do this is to, let's say we want to perform this inner product. One way to do this is to distribute the data, let's say, to 4 processors. Let's say we have 4 processors. So we send batches of the vectors to processors, and then we perform partial small inner products. And then the result of it, the result of those inner products, the partial inner products, which happen locally on this processor, we can send them to some parallel nodes. And then we sum the results on the parent node, and then we send it to the master node, and then the master node computes the final output. Okay, so this is a tree, right? So we have coordinate descent, which relies on inner products, and to perform those inner products in parallel, we have to perform a tree reduction operation. So how much does a tree reduction operation cost? Well, it depends on the length of the vector. So also the length of the depth of the binary tree, right? So in this case, if we have p processors, the depth is log p. That means we have to exchange log p messages in parallel in order to perform this inner product operation, right? So now the question is, how much each message costs? Well, a simple way to model this cost is by this linear function with respect to the number of bytes. And so what we have, every time that we want to send a message, this has a constant startup time, which we denote with the letter alpha, plus a linear term which depends on the number of bytes, where beta here is n is the number of bytes that we want to send, and beta is time that the hardware requires to for those n bytes. So, okay, so this is the communication time, right? This is the communication time that we have to pay in order to send one message. And the computational time is trivial. Essentially, it's performing an inner product, which is the length of the vector divided by the number of processors, and that gives us the total computational time. So when we put those two together, that gives the total running time for performing one iteration for single coordinate descent. Is this any questions? No? This is clear. Okay, so let's summarize what I have said so far. At each iteration, we select randomly one column from the data. We compute the partial derivative, and then we update the solution. And then we repeat the process, and this is single coordinate descent. And that costs one tree reduction per iteration. But if you remember, I said this algorithm needs a lot of iterations, right? That means we will require thousands or millions of iterations depending on the size of the data set, and that means that we require a lot of tree reductions. So although in the serial setting this method is state of the art, in the parallel setting, because of the communication cost, it's actually going to be very slow. So we hope that we can get something better, right? So what is the better thing that we hope to get? Instead of having one tree reduction per iteration, we will develop an algorithm that has one tree reduction per S iterations, where S is a user-defined parameter. And so this way we're going to defer the communication cost at each S iteration instead of every iteration. So just to summarize the result before we go into some details, we're going to decrease the startup time, this is the latency, by a factor of S, but we will pay a cost of increasing the number of bytes that the algorithm requires to converge, and we'll also increase the number of flops that the algorithm requires to converge by a factor of S. So we decrease latency by a factor of S, but we increase the bytes or the bandwidth of the algorithm and the flops by a factor of S. So if latency is the bottleneck, then we expect to see some speed-ups. Flops are distributed across the processors, and it's a nice thing that we can show that the startup time, the latency cost essentially has logarithmic dependence on the number of processors, which means that we get good scalability with respect to the number of processors. So how we're going to do this is we will view the method as a recurrence. So we have the closed form formula for computing the delta xk, the direction, at the step k plus s. So what we will do is we will unroll the formula s steps back, and when we do this, we can see that all we need to compute s iterations for this method without communicating is a bunch of inner products. In particular, we need s inner products among the chosen columns. And this is essentially a covariance matrix. So now you can probably imagine that we're going to compute the covariance matrix in parallel with one communication round instead of communicating at every iteration. We also require some inner products with the residual with the chosen columns and the residual at step k. Okay, so this is basically this is essentially algebra, right? You can unroll this formula and you can verify the results, so I will not go into these details. So what is a better algorithm? We know a priori the coordinates that are going to be selected, right? Because we can initialize with the same seed all the processors, and all processors can select the same coordinates. So we know a priori which coordinates are going to be selected. We can compute the corresponding inner products in parallel and then distribute the result to all processors. And now all processors have the necessary information in order to compute S iterations without communication. And then we repeat the process, and that costs one tree reduction per S iterations. Okay. So in terms of worst case complexity, this is what I'm about to explain. So as I said, there's no free lunch. We exchange flops for bandwidth. So we exchange flops and bandwidth for latency, and this is captured in that formula. So let me explain that formula. Alpha, beta, and gamma are the hardware parameters. Alpha is the time per message, the time that the hardware spends to send a message. Beta is the time per byte, and gamma is the time per flop. So P is the number of cores, F is a relative sparsity term, and N and Z here is a non-zero, the number of non-zeros of the matrix A of the data. H is the number of iterations of the algorithm. M is the number of columns, and N is the number of rows. So the first term is a computational cost. So the thing that you see in the parentheses is how much computation the algorithm requires in order to perform H iterations, and gamma is, as I said, the time per operation. So the term in the middle is the time that the algorithm requires for latency. So it also depends on the number of processors and the number of iterations. times the hardware parameter. And the last term is the bytes, all the words that I'm saying here that the algorithm requires to converge, times the hardware parameter again. So what you can see maybe here is that the latency in the middle term is decreased by a factor of s, while we increase the flops and the bandwidth of the algorithm by a factor of s as well. Okay, so depending on what the hardware parameters are, we expect to see some speed up or not. So if you are wondering what is the optimal parameter s, one can minimize, for example, the previous formula with respect to s, and what you get is a closed form solution, which is shown at the top. Let me simplify this a little bit. Let's assume that the matrix is extremely sparse, meaning that the gamma f and m is, this multiplication is very small. So essentially we can ignore this and we can see that the optimal s depends on the hardware parameter alpha and beta. And what I'm showing here is an example on a high-performance computer that we have at Berkeley. I found this particular hardware parameters from the documentation, and this is what I'm showing here. So we can enroll, we can avoid communication for about 100 iterations. Okay, so preliminary experiments. These are the first one is the number of the name of the data set. The second column is the number of features, or otherwise the number of columns of the data. And the third column is the number of samples, or the number of rows of the data. And the last part is a density, which you can see we have the two data sets. The first two data sets are, the first one is very sparse, the other one is dense, and we have the last two which are somewhere in between those two. Okay, so I don't know if you're wondering this, but although we essentially change the algorithm, we can show that in exact arithmetic the methods are the same, but in practice we don't have exact arithmetic, so one might expect to see some divergence between the two approaches. What I'm showing here is every line corresponds to a data set, and what you can see is that comparing the convergence behavior of the baseline versus our approach, you can see that they get similar results. So you should expect similar convergence properties in practice. In theory, their methods are identical. Okay, so I have some board statements here. I will explain this. The more processors, the better. Let me explain what that means. So what you see here on the left is the sparse data set. On the right is the dense data set. And you can see the comparison of the running time as we increase the number of processors for the baseline and hours. And as we increase the number of processors, communication increases, and that's why you start seeing maybe the baseline starts to slow down, while the blue line, which is the communication avoiding method, is more tolerant to parallel, so you can see it has a nice linear speed up as we increase the number of processors. Obviously, our method will start to slow down as well, and this is what I'm showing in these examples. You can see that the blue line also starts to stagnate at around 3,000 processors. However, it happens at much later stage comparing to the baseline, which is not a communication avoiding method. The plots are for log scale just to demonstrate the gap between the two approaches. Okay, so the running time breakdown for the sparse data set on the left and the dense data set on the right. The blue line, let me start with the red line is the total running time. And the green line is the computation requirements and the computation speed up. And the blue line is the communication speed up. So what you see here is speed up as we increase the parameter s. Here, it seems the best result seems to be when we set s equal to 64. That means that we avoid communication for 64 iterations. We get about 3 times faster in total. And communication obviously is much better, but when we aggregate the results, we get about 3 times faster. A nice result is that, empirical result is that although I said that computation is increased as well, because we can take advantage of +3 efficient local operations, we kind of maintain computation as well instead of increasing it. Similar results for other data sets, maybe slightly better. Yeah, let me move on. So yeah, that's the first part of the talk. I don't know if you have any questions before I move to kind of different subject. Yeah.
In the first graph, you mentioned an objective function. Can you tell us which one is the objective function?
So these are L1 regularized least squares. The experiments are L1 regularized least squares. Any other questions? No? Okay. All right, so I'll move to something different. This is a second project that I've been working on. This is related to graphs and optimization. We published a few papers the past 3 years on this subject. So let me start. Maybe this part of the talk is going to be more intuitive, or at least the first part of it. So what you see here is the US Senate from 1789 until 2008 in the form of a graph. So every node here is a senator, and 2 nodes are connected. Each senator serves for 2 years in Congress. And 2 senators are connected with an edge if they have similar voting pattern. So generally there is an assumption in machine learning that there must be some global property for the data sets. In this particular case, we can see that the graph separates between and after the Civil War. And actually separates also after the Civil War, where the formation of the party started between Democrats and Republicans. I don't remember which one is which, if Democrats are the top or the bottom, but the separation is clear. Now you might think that this is an artifact of the visualization. Actually, the result that you see here, the clustering result, I obtained it by using spectral clustering. Spectral clustering is when we form the Laplacian matrix of the graph, and then we are looking for the second minimum eigenvalue, eigenvector, sorry, and then we threshold the eigenvector, and that gives us this result. Okay, so there's a global property here, very clear, that is also captured by the method as well, and the visualization software. However, in practice, we've seen, especially very large data sets, is that they have there's no global structure, there's no clear global structure, but there's a lot of interesting local structure, meaning that it might be a lot of small communities instead of 2 of them. So in this particular case, what you see is a protein-protein interaction network, and every node here is a protein molecule, and 2 nodes are connected with each other if they have similar functionality. And the color is some metadata information that we have that was given to us by an expert. Okay, this is a trivial result actually. In practice, what you see is this one. So this is much more complicated, and there's clearly no global structure, but there is still some local structure that one might hope to recover. That might have important application in terms of the important impact in terms of the domain and the application. So this is also a protein-protein interaction network. And so the question now is, what I will talk about is how we can find some of these local clusters, the small communities, using local graph clustering. I will give a definition. I will introduce a state-of-the-art method, and which is a procedure, meaning that you do a few steps and then you stop. But what we will do is we will interpret this procedure as an optimization problem and then apply optimization algorithms. Okay, let's see. What is the definition of local graph clustering? So we aim to find a target cluster B, but we do this by, we want to find a set of nodes A, given a seed node, given one node in that target cluster B. So, and we want the set A to have good precision and recall with respect to the target cluster B, right? But we want, it's semi-supervised. We need one node in that target cluster B. And the algorithms that we'll discuss, the running time for finding this set of nodes A depends on N. It doesn't depend on the whole graph, right? So I'll explain what that means in terms of picture later on. So because of this property, these methods are extremely scalable to the largest available graphs, which currently is of the order of billions of nodes and edges. And generally, as a rule of thumb, I would say that these methods are good for finding a small cluster and small neighborhoods in a graph. Okay, let me give you an example. So this is a Facebook network, and every node is a student, and two nodes are connected with each other if they are friends on Facebook. And these are data from Johns Hopkins University from 2005. It's when Facebook started. These data sets do not exist anymore. You can only find them on torrents and sites like this because Facebook does not allow you to publicly distribute them. But anyway, so what I want to focus here, which I will use as an example, is this cluster of purple nodes. These are students of year 2009. And that little blob next to it on the left side is students that happen to have the same major when they were at Johns Hopkins. So when we use a global method, the Laplacian matrix, we find the second minimum eigenvector, we threshold it. Then what you get is this result here denoted with a yellow color, which is 20% of the graph, right? This combines together those two clusters, the students of year 2009 and the students that happen to have the same major. But what if you want to find one of it, right? So you can use local graph clustering. So what you do is you ask for one node in that cluster, denoted with the yellow color, and then we run the local graph clustering algorithm, and then we can find only the students that happen to have the same major, and the running time depends only on the orange nodes that you see here. It doesn't depend on the whole graph. We can do the same with the students of year 2009. Is there any question about what we're trying to do here? Okay.
So we define the neighborhoods in which we're going to search for neighborhoods.
So all I need is a seed node, right?
Okay, a seed.
A seed node, yeah. Only one node. And also, if you want to have theoretical guarantees, you also need to have a sense about how large the cluster is going to be. That will also determine the running time of the algorithm. Okay. There are ways and open problems on how to automate this because the theory comes from, I wouldn't say it's extremely useful, but at least you have a guarantee that you're going to recover the correct cluster if it exists there, right? If B exists, then, and you set the parameters correctly, then you can find a set of nodes A that is a good approximation of the target cluster B. Okay. So how do we find what is a method? A very popular one is called approximate personalized page rank. What it does, this is a toy example. What we do is we set. So let me explain first the notation. So R is the residual mass, and X is an element for every node that essentially will hold some mass that will distribute to it. So the seed node in this case is a node A, right? So someone tells us, find me a cluster around node A. We put all the mass, we put mass 1 to the residual of that node, and then we need to start the algorithm. So the first step is pick the node that has the largest residual mass, in this case is A, because that's how we initialize the algorithm, and move 10% of it, where 10% is a parameter, to X. So X gets 0.1, and the rest of it, which is 0.9, is evenly distributed to the neighbors, B and C. So each one gets 0.45. And that's one iteration. Okay, alpha is the teleportation parameter from the page rank system in terms you have seen it, if you have seen it. The next iteration is again, we repeat the process. What is the node that has the largest residual mass? In this case, they have the same, B and C, so let's say we pick B. and this is the end of iteration 2, and then we repeat the process, and this is the end of iteration 3. So you can see that as the algorithm runs, you start to distribute the initial probability mass from the seed node to the neighbors until you touch the whole graph. And the question now is, when do you stop, right? When do you stop will determine the running time of the algorithm, and will also determine the quality of the output. Okay, so now theory says that we want to stop when the maximum normalized residual, so when this ratio, the residual over the degree of a node is the number of edges of the node, is less than the constant rho times alpha. Alpha is a parameter of the algorithm, is an algorithm parameter, and rho is a termination parameter. So if rho is very large, then what will happen is we allow for a lot of residual to remain on the nodes. That means that we will terminate early. If rho is extremely small, that means we cannot allow a lot of residual mass on the node, so we will touch a big part of the graph. Okay, so there are very specific ways related to the question how you should set rho and alpha. I'm not going to discuss this today. These are a lot of details. But again, you need to have some information about what you're looking for in order to set the parameters correctly and have the theoretical guarantees. But what I will talk about is how we can, how this algorithm, this procedure, and combined with this termination criterion is related to optimization. Okay, so I won't be able to show the details, but you probably have to believe me that when you run this algorithm with that termination criterion, essentially you're solving this L1 regularized optimization problem. And I will show in the next slide the way that those two are related is through the optimality conditions of that optimization problem. Let me explain a little bit the parts of the objective function. So the first norm, P is the incidence matrix. The first norm, what it does essentially, it measures distances among nodes. Okay, so every node corresponds to an element X. So we want to measure distance. We want to measure the distance between the nodes through the representation X. Okay, so we want this to be small because if there's a cluster, we want the element X, the X's of that cluster to be the same, right? This would be a way to say that these nodes have the same value of X, so they must be in the same cluster. The other two parts are responsible for locally biasing the optimal solution. So meaning that I want the how can I explain this better? So let's see the details. So H is a diagonal matrix which is non-zero only for the seed node. So what I'm saying here is that I want the element X of the seed node to be very close to 1. And Z is a diagonal matrix which is non-zero for the rest of the nodes. So all I'm saying here is I want the rest of the nodes to have very small probability, right? So this locally biases the solution around the seed node. And the other one there appears as a sparsity inducing term, right? It's a substitute for early termination that I described here. In terms of optimality conditions, those two differ only in terms, one says I want less than equal, the other one says if my X is non-zero at optimality, I want this to hold as an equality, but if it's a 0, then I don't care, it can be an equality. Alright? So this comes from the optimality conditions of the optimization problem. So what we can show is that we can bound the volume or otherwise the sparsity of the optimal solution by 1 over rho. Rho is the regularization parameter. Let me show it again. So the larger it is, the denser the solution is going to, sorry, the sparser the solution is going to be. The smaller it is, the denser the solution. So we can actually prove this. Generally, it's not true. L1 norm is used as a heuristic for sparsity. But in this case, we can also prove that the sparsity of the optimal solution is bounded by 1 over rho. So we have a connection, nice connection between sparsity and the regularization parameter. we can show that when you solve the optimization problem, it's going to have the same combinatorial guarantees in terms of precision and recall for recovering the target cluster. And the nice thing that I'll focus in the next slides is that we replaced an algorithm with an optimization problem, and now we can solve the optimization problem however we like. Right? So pick your favorite optimization algorithm, and you can maybe black box it, let's say, this way, instead of having a specific algorithm that represents a specific model. Okay, so let's see an example of an optimization algorithm for solving the L1 regularized problem, and I will explain the algorithm in standard optimization notation. So this algorithm is called Proximal gradient descent. What it does is at every iteration you make a local approximation around the point xk of the objective function, and you use this as a way to update the parameters xk. So what we do here is we keep the regularizer g as it is. We don't do anything with it, but we make a first order approximation of the function f of the objective function, and then we add a quadratic, which is essentially an upper bound on the approximation error. So in this particular problem, this subproblem has a closed form solution, so it's very inexpensive. But what is important is how you implement it, right? So if you make a bad implementation, let me explain differently. The vector x and the gradient are going to be sparse all the way. So you have to make sure that when you implement proximal gradient descent in a clever way such that you maintain the sparsity of the parameters and the gradient. Otherwise, that means that when you implement the algorithm, you're going to touch some nodes that are not part of the node in the solution, so you just destroy the running time of the algorithm, right? So it needs some careful implementation. So this demonstrates what I've been claiming about running time. So the red line is the optimal number of non-zeros, and the black line is the number of non-zeros for proximal gradient descent. The way that the method works is it's monotonic. It only increases the number of non-zeros at each iteration. Well, it all remains the same actually. And it increases the number of non-zeros until it reaches the optimal number of non-zeros, and never touches anything that is not part of the optimal solution, right? So if there is a zero optimality, the algorithm will never touch the node, the corresponding node. Okay, so this is a little bit of moment of truth in terms of complexity. What happens when we compare the proximal gradient descent method with the state-of-the-art method that I presented initially? Unfortunately, the outcome is not very clear, in the sense that at least for unweighted graphs where we have results for both methods, it's not very clear which one is better. However, we can show that you definitely need some non-trivial analysis that we did in order to generalize the results to weighted graphs as well. So unweighted graphs are the graphs where every edge has capacity 1, so weight 1. But there is scope in the sense that we haven't explored accelerated methods yet. So let's see what to expect by an accelerated method. So the accelerated method requires much less iterations, and this is what you see here, the convergence of the method in practice. The accelerated method requires much less iterations, but it's going to touch more nodes than at optimality, right? So there's a question here. Yes, I need less iterations, but how much more am I going to touch, right? And if you do the analysis of the method in a trivial way, then what you get is the result on the right. You can see that the gradient descent method S star denotes the number of non-zeros of optimality, and nu or mi is the strong convexity parameter of the problem. And you can see that the accelerated method has square root dependence on the strong convexity parameter. But if you do the analysis trivially, you're getting killed by the fact that you can't bound the number of non-zeros. So you see that it depends on the volume of the whole graph instead of on the volume of the non-zeros of optimality. So there's hope that we can maybe improve this to depend only on the number of non-zeros of optimality, and then we'll have a clearly better algorithm. Okay, so some software that I have developed that it might be also useful to you. This software is actually part of a DARPA program, and we were asked to develop an API for local graph clustering. And generally, we were very careful to have a very useful, very easy to use interface, or we are getting there. And it's a Python code. It has C++ routines in order to guarantee that the methods are well implemented. Generally, it's scalable even on your laptop. We've tested experiments with 1 million edges on my laptop, which has 16 gigabytes of RAM. We have a lot of demonstrations on social networks, bioinformatics networks, other random networks as well. And we have a lot of Python notebooks where you can also see some of the visualizations and see what is the output of the algorithm if you want to experiment. I have video presentations, a lot of details about local graph clustering, and in total we have 12 methods and pipelines that you can use. Other software that I have developed is related to Newton-type methods and coordinate descent methods that you can also find online. And that brings me to the end. And thank you very much for your attention.
Ωραία, να ρωτήσω με κανένα να στην αρχή θα ελληνικά έτσι.
Ναι, βέβαια.
Στην αρχή μας πείσατε για την stochastic gradient, πράγματα.
Ναι, coordinate descent.
Για την coordinate descent.
Ενδιαφέρον. Η μία κάνει sample τα coordinates, η άλλη κάνει sample τη συνάρτηση.
Ωραία. Εσείς εδώ τα coordinates θα κάνετε sample τυχαία ή με κάποιο τρόπο...
Τυχαία, ναι.
Ωραία. Υπάρχει και κατανομή στη τυχαιότητα.
Σε συγκεκριμένα παραδείγματα χρησιμοποιούσαμε uniform distribution, κάθε coordinate έχει την ίδια πιθανότητα να επιλεχθεί. Αλλά υπάρχουν κάποια papers οι οποίοι χρησιμοποιούν ellipsis constants per coordinate και πολύ πρόσφατα θα πρέπει κάποιος να έδειξε κιόλας ότι αυτό είναι χρήσιμο να δείξει ότι έχει καλύτερο complexity. Αλλά δεν το έχω χρησιμοποιήσει στην πράξη αυτό.
Ωραία. Και αν κατάλαβα καλά, αυτό που κάνετε είναι ότι αναβάλλετε την ενημέρωση για L steps. Κάνετε όλες τις ενδιάμεσους υπολογισμούς που χρειαστούν και κατόπιν γίνεται το update.
Ναι, ακριβώς.
Θέλω να κάνω μια ερώτηση σε σχέση με την απλή γράφη. Αν πάτε να ρωτήσετε την απλή γράφη, σε ένα παράλληλο περιβάλλον. Εδώ καταλαβαίνετε ότι κερδίζετε κάποιο κινητικό descent ή όχι. Μπορεί να μην μπορείτε να το βάλετε τώρα, απλώς το ρωτάω γιατί δεν μπορώ να το βάλετε εγώ τώρα.
Σωστό. Θα πρέπει να κοιτάξουμε gradient descent. Θα χρειαστεί να κάνεις όλα τα inner products σε κάθε iteration. Θα έχεις ένα communication round σε κάθε iteration. Εάν η μέθοδος είναι πιο γρήγορη σε complexity, τότε ίσως είναι καλύτερη. Τώρα, υπάρχουν πάλι δύο πράγματα. Υπάρχει πράξη, υπάρχει θεωρία. Στη θεωρία, single coordinate descent, randomized single coordinate descent, είναι καλύτερη από gradient descent. Με την έννοια ότι, ας πούμε, παίρνει strongly convex πρόβλημα, έτσι. Και οι δύο μέθοδοι έχουν log 1 over epsilon dependence, αλλά το dependence στο condition number για την randomized single coordinate descent είναι καλύτερη. Δηλαδή, ναι, στα paper που έχουμε στην ουσία δείξει αυτή τη μέθοδο έχουμε ένα framework τέλος πάντων, το οποίο εφαρμόζει και σε accelerated coordinate descent και block coordinate descent και Newton type coordinate descent. Ο λόγος που διάλεξα coordinate descent ήταν μου άρεσε το γεγονός ότι είναι in worst case η πιο γρήγορη μέθοδος και ξέρω και προσωπικά και στην πράξη ότι έχω κάνει πολλά πειράματα, σε serial περιβάλλον όμως, ότι ήταν τους πιο efficient που έχω χρησιμοποιήσει. Για machine learning προβλήματα όπως regression, L2 regression, L1 regression, L1 logistic regression και τέτοιες machine learning προβλήματα. Αλλά είχε το πρόβλημα ότι όταν πήγε στο παράλληλο περιβάλλον το κάθε iteration είναι πολύ inexpensive, αλλά μετά επειδή έχεις πολλά, έχεις το bottleneck αλλού.
Και μια τελευταία ερώτηση. Όταν πάτε στο τελευταίο slide, το τελευταίο είπατε ότι υπάρχει χώρο να accelerate κάτι, στον τρόπο πιο γρήγορα και να μην πειράξω, να μην πάω σε ένα νόμο που πάω.
Ναι, ακριβώς.
Γιατί υπάρχει αυτό το χώρο. Καλό να υπάρχει.
Καλή ερώτηση. Η πραγματικότητα είναι ότι έχω προσπαθήσει 1-2 μήνες να κάνω bound αυτό το jump που έχει εκεί πέρα. Δεν τα έχω καταφέρει ακόμη.
Κάνετε bound θεωρητικά.
Ναι, δηλαδή αντί να έχω το trivial result που είναι στη μέση, να έχω από κάτω.
Αυτό προέρχεται εξαιτίας του acceleration του inertia της.
Ναι, αυτό που συμβαίνει είναι ότι ναι, έχει ένα momentum ο αλγόριθμος και τι κάνει. Το gradient descent, το απλό, μεταφέρει probability mass από το residual στα parameters. Και άμα προσθέσεις το probability mass μεταξύ το residual και το είναι πάντα ίσο με το 1. Δηλαδή, το σύστημα κατά κάποιο τρόπο έχει μια ισορροπία. Όταν κάνεις accelerated gradient descent, αυτό το extra step που έχει, είναι σαν να σου φέρει, σαν υπάρχει ένας θεός, ας πούμε, και σου λέει πάρε και λίγο extra probability mass να βάλεις. Οπότε αυτό σε βγάζει εκτός. Και μόλις βγεις εκτός, ο αλγόριθμος αρχίζει και διορθώνει. Δηλαδή, έχω καταλάβει ακριβώς που είναι το λάθος. Λάθος με την έννοια ότι. Ναι, αλλά δεν έχω καταφέρει να κάνω το bound ακόμα.
Πάντως, όταν συγκλίνει, βλέπω ότι συγκλίνει καλά.
Ναι, αυτό είναι. Ναι, έχει square root dependence στο strong convex parameter. Ο accelerated algorithm και στη θεωρία και στην πράξη έχουν πολύ λιγότερα iterations από ότι τα gradient descent.
Ήταν με την έννοια ότι με τον άδρο χρόνου zero. Κατεβαίνει αυτό το όσο.
Ναι, κάνει oscillate. Δηλαδή, μόλις ξεπεράσει, κατεβαίνει κάτω και μετά ξανανεβαίνει. Κάνει oscillate μέχρι να κάνει converge. Τώρα, δεν ξέρω, δηλαδή, δεν ξέρω αν υπάρχει κάποιο worst case example το οποίο να μην μπορώ να το κάνω bound. Αυτό θα πρέπει να κοιτάξω, πιστεύω.
Άλλες ερωτήσεις. Σας ευχαριστήσω.